When you come to an actual polymer, of course, you don't just have two angles about which you can rotate and thereby vary the energy. You have many, many angles. We saw that between each sugar residue in the DNA chain, that there were 5 single bonds that you could rotate around. And, you've got tens, hundreds, thousands, millions potentially of those individual repeats in a polymer chain. So the number of possible arrangements that you can get is absolutely astronomical, and you can't represent them in a simple 3-dimensional plot anymore. But qualitatively, we can still use this idea of a sort of energy landscape to discuss what's going on. So this is just a simple idea that you can have lots and lots of possible minima corresponding to relatively favourable states and maxima corresponding to less favourable states in between, corresponding to different combinations of those angles of rotation. But so long as the heights of the hills, so in other words, the difference between the most favourable states in the bottoms of these dips and the least favourable states at the top, so long as that energy gap is comparable to the average molecular energy, then it's going to be quite easy for the molecule to move from one structure to another. In other words, it's going to continue to be flexible, and it's not going to have a strong preference for a particular state, particularly if, as in this example, there are lots of these minima with similar energies. Then there's no reason why the molecule should prefer one to another. So it's going to be a flexible structure which will keep jumping from one structure to another. And that will be the case for lots of polymers that don't have strong preferences for a particular structure as a result of intermolecular forces. This is the grave of Ludwig Boltzmann. Next time you're passing through Vienna, you should go and visit him in the central graveyard there, because he deserves it. He was a tremendously great man. Not only, as you can see, did he have the most impressive pair of shoulders of anyone in the history of physical science, he also was the person who really, I think, transformed chemistry from being a branch of cookery to being a branch of physical science. And he did that by realizing that chemistry is all about statistics. So he appreciated this idea that we've already talked about, that energy will always tend to become dispersed among all the possible states that it has access to. It's a natural tendency of energy that it doesn't stay localized in any one particular state, but it tends to spread out. And he realized that, and he thought a lot about the implications of it. And you can always tell when you've really made it in science, because you get on your tombstone, instead of some sort of trite epitaph, you get this, your equation. Okay, S equals K log W is Boltzmann's equation. And what that basically does is define a quantity. S stands for something called entropy. And although entropy had been defined before, he was the person who really understood what it meant and came up with this statistical interpretation of it. W is in effect the number of different ways that energy could be distributed in a given state of a system. So in the case of our polymer that we were looking at a moment ago, where we saw that it could sample all sorts of different spatial arrangements, W is going to be a very big number, because all these different spatial arrangements will contribute to the number of different ways the energy can be distributed. And what he realized, therefore, is that if you have more than one possible state, so if you have, for example, in the case of DNA, which is what we're going to be talking about, you have the double helical state, and then you have an unfolded state, which would be more like the random polymer that we've just talked about. What he realized is that the one which is going to be more stable is going to be the one where the energy is most widely distributed. And so entropy has a hugely important place in chemistry for that reason. So what we need to do is to think about entropy, the dispersal of energy, specifically in the context of the DNA double helix. So we can think about the folding of DNA in a quite simplified, but I think useful way, as a chemical equilibrium just between two states. The folded state, which is the double helix, and an unfolded state. So in the double helical state, it's essentially restricted to this one specific structure. Now that is oversimplified. In reality, that structure will wiggle. In other words, there is some dynamic fluctuation around that equilibrium position. But as a reasonable approximation, we can say that the folded double helical structure is a specific arrangement of atoms. The unfolded state differs first of all and crucially in that the two chains are now separate. And so what that will mean is that the dynamic movements of atoms in this chain have no influence now on the atoms in that one, whereas here, obviously, one chain can't move without the other one moving as well, otherwise the structure's not remaining in the double helical form. But secondly, within each chain, there's also much greater conformational freedom. It can change its shape because it's not required to have all the atoms arranged in this specific way that we have here to make the intermolecular forces that hold this together. Now, this really is an oversimplification. There's lots of evidence that shows that single-stranded DNA is not a completely random coil and that it does have conformational preferences. But it's not nearly as strong as this. It has a great deal more conformational freedom than you would have in the folded state. So we can think of this in terms then of what it looks like on an energy landscape. Now, if the last picture was a bit of an oversimplification, this one is a complete flight of fancy, so please don't be misled. This is not some kind of complex calculation. This is just a complete artist's impression of an energy landscape. And remember that if you've got a polymer like DNA with lots and lots of flexible bonds, each of which has some kind of freedom of rotation potentially, then you can't represent it on just a three-dimensional plot. If you had 100 rotatable bonds, you'd need a 101-dimensional picture to represent the energy landscape, and obviously that's not achievable. So this is purely a means to kind of try to get your mind around what the issue is, rather than an actual calculation or anything. So the point is that this extended ribbon is meant to represent the fact that a long polymer chain, like a DNA molecule, can potentially have a huge number of possible arrangements in terms of the combination of bond angles that, rotational angles that are formed around the bonds. And as in the simpler energy landscape that we looked at before, through most of this ribbon, although it's bumpy, the difference in height between the peaks and the declivities is quite small. So the peaks arise, as we saw, as a result of atoms getting in each other's way. So we saw that when we looked at butane and pentane. It comes from repulsive interactions when atoms are a little bit too close for comfort. And some of the troughs are simply what you get when those interactions are minimized, but some slightly deeper ones could be formed where you actually have some favorable interactions. So, for example, you could imagine a couple of the bases in DNA coming close together and forming some kind of favorable, attractive intermolecular force, and that would lower the energy a bit. But the point is that the actual energies involved here are quite small, and so there's a great deal of flexibility. In other words, if the chain is in this particular arrangement, at some point it will very easily acquire enough energy to move on to there and then on to there and so on, and it can just move around and sample all sorts of conformations quite readily, because the energy changes involved in moving around the landscape are very small. And it's therefore a reasonable thing to define this whole combination of possible angles as a state. So we can think of a state as being that set of arrangements of the molecule in space which can rapidly interconvert with one another just by energy transfers along the chain and with the surroundings. The bit that doesn't fit in with all of that is this very localized bit here, because you can see that if you happen to come up with this particular combination of bond angles, your energy actually plummets and you arrive in a much lower energy state. So this represents the double helical conformation. So what we have on this diagram is basically a two-state system, where nearly all of this space is just this bumpy energy landscape with small hills and declivities, and that's our unfolded state. And then this very localized region where you have a very narrowly defined range of possible angles, that's the double helical conformation. And what we need to do is to see how this kind of picture feeds into letting us understand how that equilibrium is going to work. One way to think about this is to imagine yourself as a DNA molecule wandering around through this energy landscape. And because of its vastness, this extended ribbon, which represents the energy landscape for the unfolded state, you could spend a huge amount of time here just wandering around exploring all the different possible states. And that's the statistical thing. That's the advantage that the unfolded state has in terms of statistics, that because there are so many possible arrangements of the energy that's available here, it has a big advantage in terms of entropy. But then as you're doing your wandering around, you may just by chance come to here, and then you're going to tumble over the precipice and fall into this abyss down here. So in other words, you've arrived at the folded double helical state. And you can see that now you don't have this freedom to wander around over lots of different structures anymore. So it doesn't have the statistical advantage that you had before, because you're basically trapped down at the bottom of this well. And the only way you're going to get out again is if, by chance, you get enough energy to let you climb back up the sides and back into the folded state. So you can think of this as a sort of trap in the landscape that you fall into. And the reason this might be the state where you spend most of your time might be because the chances of getting enough energy to climb back out again are quite limited. So that sort of really begs the question, what do we mean the chances of getting energy? You know, where is this energy coming from and going to as you move around over the landscape? And of course, what you have to realize is that a DNA molecule doesn't exist in splendid isolation. It's part of the universe. And so the energy comes from and goes to the rest of the universe as you move around over the landscape. So, for example, as you are moving around here and you suddenly arrive at the precipice and fall down here, you're moving to a state of lower energy. In other words, it's an exothermic process as you do that. And you know what happens in an exothermic reaction, which is that as the system moves to a lower energy state, the energy that's released is released in the form of heat. Now, what does heat mean? Well, heat means energy that's distributed around the rest of the universe. Okay, it's not energy that's localized in any specific form. It's spread out amongst all the molecules in the surroundings, and it's spread out amongst all the different types of energy that they could possibly have. It's disorganized energy, if you like. And so what happens is that when the molecule falls into the abyss that corresponds to the double helical state, energy is released to the surroundings, to the rest of the universe. Now, what does that mean in entropy terms? Now, the entropy of the DNA itself is clearly now massively reduced, because the number of different ways you can arrange the energy, if you're confined to this very localized region of the possible conformational space, that entropy is going to be very small. However, if you've released all this energy into the surroundings, that means there's more energy that can be spread out around the rest of the universe. And of course, there is then a huge possibility for the different ways that energy can be spread out. So although the entropy of the DNA decreases, the entropy of the wider universe can increase. And that's really what the position of equilibrium comes down to. Okay, the folded state will be favorable if the entropy of the universe as a whole increases as a result, because even though the DNA's own entropy has decreased by getting pinned down to this localized region of conformational space, the rest of the universe has benefited from the energy released and has more energy to spread around the near infinite number of possible energy levels in the wider universe. And so the question is whether that increase in entropy of the surroundings can override the decrease in the entropy of the DNA. And that's going to depend on how deep that well is, because the more heat is given out, in other words, the lower the energy of the double helical state, the more heat will be given out, the more that can be dispersed around the rest of the universe, and the more favorable, therefore, the folded state becomes. So that sets us up for where we want to go next, which is to examine the interactions which cause this double helical state to have a lower energy than all these other possible arrangements which collectively represent the unfolded state. And it's important that we think of it in those terms. It's not just about looking at what interactions are formed within the folded double helical state. It's a case of comparing those with the interactions that could be formed in all these other arrangements, which collectively we're calling the unfolded state. Now, there is one massive gap in this picture that we've set up here, and that is that we've ignored the solvent. Okay, DNA doesn't fold up in a vacuum. It folds up in aqueous solution. And we haven't thought at all about what about the energy of the water, and indeed, what about the entropy of the water? How is that affected by the folding up of the DNA? And in the case of the energy, that's something we're absolutely going to think a lot about, because we can't ignore that. It's not just the DNA that matters, it's the effect that it has on the solvent, the water that it's dissolved in, that matters too. The entropy of the water also actually matters a lot, and it's something we'll talk a little bit about later on, but actually it's really quite important when it comes to accounting quantitatively for these things. And it's a topic that people working in this area of research get quite hot under the collar about. I know this because I used to be one. And it is a real complication because it's quite difficult to understand precisely what the solvent is doing. You know, the solvent is a liquid. It doesn't have a defined structure in the way that the DNA does. And so thinking about how disordered is the solvent, how much entropy is there associated with different possible arrangements of energy within the solvent, is a very hard thing to do. So we're not going to spend too much time actually thinking about that, but just be aware at the back of your mind that that is a part of the picture as well. Okay, so now then we're set to return to thinking about what it is that drives this equilibrium over in this direction and makes the double helical state favourable. And so what we're going to do in the next section is to look in detail at the intermolecular forces which are present in this state, but also think about how those would compare with the forces present in this state, and all the time remembering that this whole thing is sitting in a bath of water, as are these. And so the interactions with the water are every bit as important as the interactions within the DNA molecule itself.